All right, let's talk about the hidden architecture of our world, materials. Today, we're going to explore how human innovation isn't just about big ideas, but about the very stuff we use to make those ideas real. So let's start with something you probably have in your pocket, a smartphone. It looks sleek and simple, right? But if you could crack it open, you'd find a whole universe of materials, a complex symphony of elements, from the lithium in the battery to the rare earths making the screen light up, all of it meticulously engineered into alloys, glasses, and composites. Every single piece is a testament to how well we've mastered the stuff our world is made of. So that begs the question, right? How do we get from, chipping away at a piece of flint to fabricating flawless silicon wafers? It's not just a simple timeline of one discovery after another. It's a story about ambition, hitting a wall, and then finally breaking through. To really get a handle on this history, we need one core idea, and it's this. Every great human ambition, whether it's building a skyscraper that touches the clouds, a jet that breaks the sound barrier, or even a quantum computer, it always, inevitably, slams into a material ceiling, a fundamental limit based on the materials we have to work with. This idea, the material ceiling, is gonna be our guide. It shows us that progress isn't some steady, gradual climb. It's more like a series of explosions where each leap forward is ignited by shattering one of these material barriers. So, how do we shatter these ceilings? Well, the key is understanding something called the materials tetrahedron. Think of it like the Rosetta Stone for material science. It shows us the 4 interconnected pieces of the puzzle that we need to play with to unlock the next big thing. Okay, now here's where it gets really interesting. These 4 things are all connected. It's like a delicate dance. If you tweak one, you change everything else. For example, if you rearrange the atomic structure, you can completely transform its properties, say, make it way stronger. If you invent a new way of processing it, you can unlock totally new structures and properties. And all of that determines its final performance, whether it's in a jet engine or a computer chip. The real breakthroughs happen when we master this whole dance. So let's put this idea to the test. Our first stop, the Industrial Revolution. The big ambition then was mass production, making things on a scale nobody had ever seen before. But that ambition was literally forged in fire, and it hit a molten hot ceiling. 1,500 degrees Celsius. That was the magic number. It was the insane temperature that blast furnaces in the 15th century needed to hit to turn iron ore into liquid metal. But getting that hot created a massive, massive problem. So here was the issue. The furnaces themselves, which were built out of the strongest natural stone and clay they had, would just fail. They'd melt or crack under the same intense heat they were trying to contain. It was like trying to carry water in a paper bag. That right there was the material ceiling of the industrial age. And the breakthrough? You might think it was a new kind of metal, but nope. It was a completely revolutionary type of ceramic, synthetic refractories. These were some of the first materials ever designed specifically to tame that kind of inferno. They could handle the heat, contain the fire, and let furnaces burn hotter and longer. And that unlocked the flood of metal and glass that powered the entire Industrial Revolution. And this is the direct result of that breakthrough. Taming fire back in the 15th century eventually led to the kind of precision we have today. We have advanced processes like this one, ladle metallurgy, where we can literally fine-tune the composition of steel, creating these incredible high-performance alloys. Without breaking that old heat ceiling, the steel that makes up the backbone of our world, our railways, our bridges, our skyscrapers, it would all still just be an idea on a piece of paper. Okay, so from the fire and fury of the Industrial Revolution, let's soar into the 20th century. A new dream takes hold, conquering the skies. But this dream hit a totally new kind of ceiling. The challenge wasn't about taming fire anymore. It was about defying gravity. You can see the problem right here. Steel was the champion of the industrial age, no doubt, super strong, but it was just too heavy for flight. Then along comes this new contender, duralumin. It was this game-changing aluminum alloy that combined the lightness of aluminum with the strength of steel. This was the material that gave us wings. It completely shattered the weight ceiling and kicked off the age of aviation. And this marks a really profound turning point in our story. For thousands of years, we were basically just sculptors, taking the materials nature gave us and shaping them. But now, with alloys like duralumin and the rise of polymer chemistry, we became architects. We were designing and building brand new materials, atom by atom, derived from air, coal, and water.
This wasn't just some slick marketing line for nylon, DuPont's synthetic silk. No, it was basically a declaration of independence. It was proof that we were in a new era where chemists could cook up new materials from the most basic building blocks. Materials designed to solve a very specific problem, like a country not wanting to rely on imported silk. We weren't just discovering the world anymore. We were starting to invent it. Okay, now let's leap forward to the middle of the 20th century, right to the dawn of the digital age. The ambition this time? To build a thinking machine, a silicon brain. But the material ceiling was this frustrating, unreliable ghost in the machine, the problem of controlling the flow of electricity. Just look at the difference here. On the left, you've got the vacuum tube. It was this bulky, power-hungry beast that was the heart of early electronics, and it burned out constantly. Imagine a computer with thousands of these things. It would be the size of a room and always on the verge of breaking down. On the right, the silicon wafer, the material that finally got rid of that ghost in the machine and shattered the ceiling of unreliability.
You see, the breakthrough wasn't just discovering silicon. The real magic was learning how to tame it. We figured out that silicon is a semiconductor, which meant we could learn to control its electrical properties with incredible precision. Through a process called doping, we could turn it into a tiny, reliable, solid-state switch, the transistor. And that one invention, the transistor, became the foundation for everything, the integrated circuits that are the beating heart of our entire digital world.
And that brings us to today. We've conquered heat, we've defied gravity, we've mastered information. So what ceiling is left? Well, maybe the toughest one of all. The slow, random, and often frustrating process of discovery itself. For centuries, finding new materials was basically a game of chance. A whole lot of trial and error and a few happy accidents. But the Materials Genome Initiative is trying to change the rules of the game entirely. The goal is to turn the art of discovery into a science, to go from relying on chance to designing with intention. So how does this new approach actually work? It's basically a three-step process. First, we use AI and powerful computers to dream up millions of potential new materials and predict their properties before we ever even make them. Second, we build this massive shared library of knowledge, so every experiment and discovery can be built upon by everyone else. And third, we have these self-driving labs, fleets of robots that can test our AI's ideas at a crazy speed, creating this powerful feedback loop between the digital world and the physical one. And this isn't science fiction. This is happening right now. We're using the same kinds of AI that can create incredible art or write poetry to literally design new materials from the ground up. This is the beginning of what's called inverse design, where we start with the problem we want to solve, and then we ask the AI to invent the perfect material to solve it. This is the ultimate shift in thinking. For all of human history, we've been explorers, finding a new material and then figuring out, okay, what can this thing do? Now we're becoming architects. We can start with the dream, like a perfect artificial heart that never wears out, and then use these new tools to actually design and build it, atom by atom. We started this whole journey talking about ambition, and we're going to end with a question. We've smashed the ceilings of heat, of weight, of information. The last real ceiling is just our own imagination. So now that we're gaining the power to create just about any material we can dream up, the question isn't what can we build anymore, it's what kind of world do we want to create?